Okay, good day everybody. So, we will start the linear algebra. So, we will start with the vector space, definition of a vector space. So, for that we need to define a external composition or external operations. So, what is the external composition? We know the binary, it's a, we know the internal composition, like we know if we have a set S. Now, we know this binary operator. It is a, we take two elements from A B, from S, then we operate this, then we get another element in A if it is closure. Okay, so this is a internal composition, like both the elements are coming from the same set, but instead of that, if one of this set is different, I mean if this, so like if we have a function like f cross v to v, where f and v are two non-empty subset R 2 non-empty set. Then this type of function is called external composition. So, that means we take two elements, one is from A f, one is from f, another one is from v. So, we can write as this. Usually this is called vector, set of vector, I mean this, that is why we use this, but anyway if you do not like, you can just use x, Ax, then this will be, say, this will be member of V. Okay. So, it is basically we take a two set f and v, then it will give us a, if we operate this, it will give us a element of v. So, this is called external composition. Okay. For example, say if we have a if we have say R 3, R 3 is basically x y z, where x y z are coming from R. R 2, you know, R 2 is the Cartesian, this R cross R. So, this is basically x comma y, where x y are real number, R 3 is the 3 tuple. So, if we take this as a v, so v is basically R 3, these are our real number x y z are coming from the real number. I just denote this by, to distinguish between this as a vector, I mean vector means this is an element of these 3 tuples and these are the x y z are the real number. Now, if we take the f to be just the real number over this, I mean on real number we have this operation. Okay. Now, we define the operation multiplication we call, this is we can denote by this, this is a f, I mean R cross R 3 to R 3. So, how we do that? So, we take a and we take a vector x y z, this is also called vector, this is a 3 tuple. So, this is nothing but a x, a y, a z. Okay. So, this is an example of external operator, external composition or external operator. Okay. Basically, we have two different set, and if we operate this, it is giving us this element in this set. So, for defining vector space, we need to have such operator, such composition. We can have another example on matrix, then we can do the matrix multiplication with the some element from the matrix. So, these are the example. So, now we formally define what do we mean by a vector space over a scalar. So, for that let us take a set V let V be a non-empty set and the elements are of V usually called vector. I mean just a name, it is a set, elements are usually called vector because we are talking a name is vector space. Okay, and we have a binary composition on this V. This is a binary composition and we have a field. So, this vector space is over a field. We define a vector space always over some field. So, this is the underlined field. Okay. So, it has two operator plus and dot, this is the field plus field dot and this is the vector plus we can say. And we know the definition of the field, this will form a abelian group with plus, this will form a other than the 0 is the additive identity, this will form another abelian group and we have the distributed law between dot and plus. So, those properties are there for the field. Okay, and along with this we have a external composition, this is also called scalar multiplication with a vector. This is basically V cross F cross V to this. So, that means we take a from F and we take a vector from V. So, A we operate x, this will give us a vector, some vector in V. Okay. So, this is this is a there should exist such a external composition, this is also called scalar multiplication. So, now if certain properties satisfy with this operator, then it is called a field over the vector space over this field. So, what are those property? We will define that. So, properties are basically so let us just draw the picture. This is our V, this is our F and in F we have two operator and we have a vector addition and we have another operator which is taking one element from here, another element from here and which is giving another element of here. Okay. Anyway, so this is so first one is this must be an abelian group, is an commutative group. This is the condition that F will be a vector space over this. So, there are few conditions are there. This must be abelian group and we have few more properties with this scalar multiplication with this operator. So, first of all this has to be closure. So, A if we operate with x, this must belongs to V and this must true for all A coming from this and for all x coming from V. That means, if we take any scalar A and if we take a vector x, then if we operate with this operator, then this will be a element in V. So, this will be another vector. So, this is the this is telling the closure property of this operator. Okay. Now, few more properties on this scalar multiplication along with this plus vector plus. Okay. So, A B and if we operate on x, this should give us A dot B x. We have to understand this. So, this is a vector, this is a scalar. So, scalar multiplication, then this will give a vector. If it is giving a vector, then we can take another scalar and we can operate this will give a vector. So, that vector should be same as, so A is a field element, B is a field element. So, this is the field multiplication. So, this will be again a field element. So, this is a field element. So, that should be equal to, and this is a vector. So, this is, and this should be for all A B belongs to F and X belongs to V. Okay. This is one of the property. Another property is say A X operate with Y. So, this should be equal to A operate with X, then A operate with Y, and this must true for all X, Y and A. This must true for all A B belongs to F and all, so only A is there, all X, Y belongs to V. Okay. Now, another property is, so say A plus B, and if we operate with some vector X. So, this is the field plus. So, this will be equal to A operate with X, this is the vector plus, B operate with X. Okay. And then 1 is the field additive identity. If we operate 1 with any vector, this will give us, this is the definition. I mean, we should have this property in order to we call this V to be a vector space over the field F. So, this is for all X belongs to V, and where 1 is the additive identity, in F. Okay. So, if this all property satisfy, so this V has to be a abelian group with this operation, with this binary operation plus, this is called vector addition. Okay. And then we have on the scalar multiplication, we should have these properties. Then we say this algebraic structure V, then we say this algebraic structure V along with this F will form a vector space. So, V, this F, we have, these are the operator with F is a vector space over the field F. So, this is the definition of vector space. So, if a set non-empty set V along with a non-empty field F having this satisfy these properties, then this algebraic structure is called a vector space over the field F. Okay. So, now we will take some example of vector space. So, again this is a abelian group, means this is having 5 properties. What are those? Let us just write those before we go to the example. So, this is abelian group, means we have 5 properties like closure property. So, if you take 2 vector, then this must be belongs to V for all X, Y belongs to V. This is the closure property. Associativity property. So, if you take 3 vector X, Y, Z, then this must be, this operator must be associative. So, this is true for all X, Y, Z. Then the identity, existence of identity. So, we must have a identity element. So, we must have some vector, say 0 vector. We use this symbol to distinguish this field 0, additive 0 and this vector 0. So, such that this plus if you take any other vector is equal to x bar, and this must true for all x, and inverse. So, there must exist, every element must have the inverse under this operator. So, for x there must exist a minus x, we can say minus x is the symbol for the inverse, because this is sort of additive sense such that x minus x equal to 0 vector identity element. And then since it is abelian, we have the commutative property that x y must be equal to y x, and this is true for all x y. So, if these 3, 4, 5 properties satisfy, then this is a abelian group. So, this has to be abelian group, along with that we must have that property on the scalar multiplication. Now, we will take some example on the example of vector space. Okay. So, let us take some example. Say we take a field to be R, real field. So, this is our field F, we have a real number system, real field R. Now, if you take the R3 or R2, say R3, say x, y, z, where x, y are the real numbers, x, y, z are the real numbers. Okay. Now, we can define two operator like vector addition. So, this is our V. So, how to define vector addition? We can take just two vector, say x vector, which is say x1, x2, x3 from V, and we can take y vector, which is y1, y2, y3 from V. Now, we can define this by simply x1 plus x. These are the field plus, because these are the field element. Okay. This can be defined for any field. Instead of R, we can have any general field, but for simplicity we are taking R. So, x1 y1 plus x2 y2 plus x3 y3. So, this is just the coordinate wise sum. This is how we define the this operation. And how we define this scalar multiplication? So, we can define scalar multiplication as this. So, we can take a scalar and we can take a vector x. So, this is nothing but a x1, a x2, a x3. Okay. So, this is the way we define this scalar multiplication over the vector. Now, we can show that this will form a vector space over the real field. So, this is called real vector space, vector space over the real field. Okay, how to show that? So, for that we need to show, first of all, this is a abelian group, that V. So, basically R3 along with this is a abelian group we need to show, abelian group. So, first of all, it is a closure property, because this is, if we add two vector, it is again a member of R3. So, closure property is satisfied. Okay. So, closure property is satisfied. Now, the associativity also satisfied, because that is so associativity means if we take 3 vector x, y, z, then x bar, this we can easily see. This will come from the associate property of this plus over the real number, okay, because this is again a field. So, this is again a group. So, that means with the plus over R. So, this is there also we have the associativity property. Okay. So, now this is associativity is okay. Then the identity element is basically 0 0 0. So, that is we have 0 0 0 vector. So, that is the identity element, because if we operate with this any other vector, this will give us x. So, this is the identity element. Now, what about inverse? If you take x, x1, x2, x3, then we have a we can have minus x, which is basically minus x1, minus x2, minus x3, such that if we operate these two, this will give us a 0 vector. Okay. So, this is the existence of inverse for each element, and also we have abelian property is satisfied because, so this is the fifth property, because if we operate x, this can be easily checked, because this is the abelian property of the field plus, because this is ultimately will be the field plus. So, that is the, so this is an abelian group, and we can easily verify the remaining properties of the with the scalar multiplication, and then we can say that this is a vector space. So, R3 along with this is a vector space over R, over the real number R. This is one example. Not only R3, any R to the power n, R to the power n. So, this is basically n tuple where xi is belongs to R. This is also we can show R to the power n, R is greater than equal to 1. Again we define the similar way over this is a vector space over R. This is the real vector space. Now, we take another two vector space over R. Say we can take a polynomial of degree n. So, say V is the set of polynomial of degree n. So, a0 plus a1x plus a2x square a n x to the power n. Okay. And these a I are coming from R. These are the so this is the polynomial set of all polynomial of degree up to degree n, up to degree n. So, maximum degree is n. Now, if you take two, then how we define this plus? Now, if you take two polynomials, say p x and q x, okay, then so say p x or say a x, yeah, p x is say p x is small p x, summation of a I x to the power I is equal to 0 to n, and q x a summation of b I x to the power I is equal to 0 to n up to, I mean. So, now how we define the plus? Just the corresponding summation of a I plus b I, because these are all, this is the plus over the field R x to the power I, and this we can define over any field other than the real, this polynomial. So, we just need to have a field, then this will be the field addition in that field. So, this is, we can again show this set along with the, if we have any field also this will work. This is a vector space, this V will form a vector space over this field. So, this is called polynomial space, and we have another example of vector space like matrices. We can have set of matrices of size m cross n. So, we can have a matrix as A11, A12, A1n, A21, A22, A2n, AM1, AM2, AMN. So, we know this is the way, this is called a matrix of size m cross n. So, this is we can denote by Aij m cross n. This is the ijth element of this matrix. This is the ith row, jth column, and this is Aij. This is how we define a matrix, a storage. Okay. Now, we consider all the collection of, so these are all real numbers or these are all coming from any field. Okay. For simplicity, let us take these are all coming from real number. So, this is a real matrix. Then we can define a plus over this matrix. So, if we have two matrices, say A B, A is a matrix, So, this is of size same size, B is another matrix, then the matrix plus is basically corresponding plus Bij. This is the matrix addition we know. If we take another matrix here B, so we take the corresponding, we add the corresponding element and it will form a matrix addition. Then the scalar multiplication with the matrix is also simple, because if you take a matrix M, like this is A matrix, then how we define the scalar multiplication? We can take a scalar or a real number, say A. So, A is basically Aij. So, we just multiply A with all the elements, okay, like this. So, A into Aij, this is the field multiplication. Okay. So, this way we define this scalar multiplication. So, now we can easily verify that this set of all matrix M along with this plus this, and we are talking about real field, but this could be any other field. This can work out for any other field, is a vector space over the field. Here we are taking real field, but again it could be any other field. Okay. So, this is another example of a vector space. So, now in the next class we will discuss some properties of the vector space, then we will define the subspaces, linear span. So, we will talk about in the next class. Thank you.